We present Hunter, unsupervised human-centric 3D detection via transferring knowledge from synthetic instances to real scenes. An unsupervised 3D detection method for human-centric scenarios by transferring the knowledge from synthetic human instances to real scenes. The field of 3D scene understanding in human-centric scenarios has garnered increasing attention in recent years, owing to its pivotal role in the advancement of research on humanoid robots, assistive robots, and human-robot collaboration. LiDARs are commonly used in 3D scene understanding. Human-centric perception presents a formidable challenge. Unlike the relative regular object distribution and background context in traffic scenarios, real-life human-centric settings encompass a vast spectrum of indoor and outdoor environments with intricate and diverse backgrounds. Moreover, unlike rigid vehicles, humans exhibit ever-changing poses, movements, and trajectories, and engage in multifaceted interactions with objects and their surroundings. All these factors cause difficulties for data acquisition and data annotation, concurrently posing challenges to the precision and generalization capacity of perception methodologies. Therefore, the research for effective, unsupervised methods of human-centric 3D perception becomes necessary and imperative. Motivation. Current mainstream methods for unsupervised 3D detection can be categorized into two paradigms. One relies on motion information such as scene flow to discriminate between foreground and background elements. However, these methods encounter limitations when confronted with static objects. The other harnesses point clustering algorithms to derive pseudo-labels for subsequent iterative self-training. Nevertheless, these pseudo-labels tend to exhibit poor quality in human-centric scenarios and making the self-learning process worse and worse. That is because humans usually have sparse points captured by LiDAR, and humans may stay very close with others, all presenting considerable challenges for clustering algorithms to distinguish human instances effectively. Furthermore, for all these methods, they cannot furnish semantic information for detected objects, necessitating additional classifiers to identify the human class. Indeed, humans exhibit an impressive ability to detect objects in 3D spaces based solely on their knowledge of object shapes and sizes, since we can generate arbitrary human instances by the parametric model. This prompts us to ponder the following question: can our AI method detect human instances in 3D scenes without any scene-level annotations, merely relying on synthetic human models? To achieve this, we must address three pivotal challenges: the unification of disparate data representations of mesh models and LiDAR point clouds, the alignment of dissimilar feature distributions of synthetic humans and real humans, and the exploitation of prior knowledge specific to the human body to enhance perceptual acuity. Methods. Our method mainly contains three stages, including instance-to-scene representation transfer, synthetic to real feature alignment, and fine-grained perception enhancement. For the first stage, we exploit the inherent class-aware attributes of simulated human instances to generate pseudo-labels for real humans. In the second stage, we utilize bidirectional multi-object tracking to filter out low-quality pseudo-labels. Then we conduct feature alignment to bridge the gap between synthetic humans and real-world captured humans. For the third stage, we integrate the human body skeleton as supervision to enhance fine-grained feature learning, which can tackle more challenging cases such as human with severe occlusions. Following the common sense of the real human locations in the scene, we randomly place the synthetic human instance on the ground. Specifically, we employ ransack to obtain the ground point cloud data. Afterwards, we place selected synthetic human instances on randomly selected ground locations. To ensure the inserted human instances obey the real LiDAR point distribution, we simulate a LiDAR system to obtain the sparse human point cloud. To generate scenes that adhere to the view-dependent property of LiDAR point cloud, we simulate the external occlusions by other instances or objects in the scene for inserted humans. Specifically, we utilize the range image to achieve this. We first transform the point cloud of 3D scene and the point cloud of inserted human into the range image. Then we merge two range images based on the distance to LiDAR to insert a synthetic human instance into the scene. We employ mass-constrained receptive field control to guide the model's training. While our first stage effectively generates synthetic data with a high degree of naturalness, a domain gap exists between synthetic and real humans in aspects such as clothing, pose distribution, and overall shape. In stage 2, we utilize BEV feature alignment to narrow the gap in order to augment the detector's ability to detect real humans. To reduce false alignment, we first utilize a bidirectional filter to select high-quality pseudo-labels for feature alignment. After stage 2, the global features of real humans become close to these of synthetic humans, and we can further transfer more fine-grained knowledge of synthetic data to enhance the capability of model to identify detailed human-specific features. In stage 3, we improve the detection performance by transferring human structural semantics to the model. We also update the receptive field based on previous stages' pseudo-labels. After previous 3 stages, we have obtained relative high-quality pseudo-labels. To make the detector further converge to identify features of real humans, we fine-tune the model based on raw point cloud data and pseudo-label supervision and obtain the final results. Result. We provide comparison against SOTA methods on HuCenLife and STCrowd. We conduct experiments against 3 unsupervised detection baselines: DBScan, Modest, and Oyster. Our method surpasses Modest by 87.8% and Oyster by 86.5% in terms of MAP on HuCenLife. Our method performs closely to fully supervised method and dominates the table on STCrowd too. The third table provides our ablation study results. Our method's effectiveness is proved in that table. Qualitative results. We provide qualitative results on both HuCenLife and STCrowd. Oyster and DB scan, they suffer a lot from false positive detection, shown as orange boxes. Unlike our approach, they are class agnostic, which consider all the objects after clustering as human, such as walls, television, and even ground that failed to be removed from ground removal process. Modest, it relies on motion detector to produce and filter pseudo-labels in human-centric detection. The challenge arises from the relatively small amplitude of human movements and the possibility that only a portion of the person's body is in motion. As a result, motion detector provides bounding box with error in size and position in these scenario, shown as black boxes. Furthermore, Oyster, Modest, and DB scan all suffers from false negative detection for the same reason, shown as purple boxes. Thanks for watching.